We're picking up with the start of chapter 14 today. The lecture video I posted yesterday covered section 14.1 and a little bit of 14.2. And so we're going to look at some examples trying to make more sense of what's going on in chapter 14. Now, just worth remembering, this chapter 14 content is not relevant to the test on Thursday. So you don't have to, memorize any of these formulas or make a note card. This will be irrelevant with the second test. I guess I should call it test 3. The last test we'll have at the end of the semester. Now, what chapter 14 does is it generalizes some of the ideas in chapter 13. Chapter 13, we introduced the idea of a sampling distribution and specifically focused on how the sample proportion varies from one sample to another sample. If 3 people take samples of size 100 and each one calculates a success proportion, they're going to get 3 different numbers. But we were looking at how are those related to the population, how far would we expect them to be from one another, etc. Chapter 14 takes that same idea and applies it to the sample mean or the sample average. So now you can imagine multiple people taking samples. Let's say I send everyone in class out to go and collect a sample of size 50. Everyone samples 50 TCU students, asks for their GPA and calculates an average. So everyone in class would come back and report a slightly different average GPA. What can we say about that collection of averages? That collection of averages we talk about as the sampling distribution of the sample mean. So example problem 1 says this population or hypothetical population that we're sampling from is skewed right, has a mean of 20 and has a standard deviation of 8. Someone's going to take a sample from this population and calculate the sample mean. And so our first sub-question, part A, says if the sample size is 5, calculate the mean and the standard deviation of the sampling distribution. Also state whether you would expect the sampling distribution to be normally distributed. So here is where you need to pay close attention because questions can ask for a mean and a standard deviation of a sampling distribution now, and it could pertain to 2 different quantities. It could still be referring to a sample proportion, and then you have formulas in terms of p hat, or it could be referring to the sample mean. And if it's referring to the sample mean, as it is in this case, then the mean of the sampling distribution is just given by mu. That value is 20. And the standard deviation of the sampling distribution, that is given by sigma over square root of n. So in this case, sigma, our standard deviation is 8. We have to divide that by the square root of 5, which is our 5 is our sample size. So that's equivalent to 8 divided by 2.2361. And if you do that division, round it to 2 decimals, we get a standard deviation of 3.58. So these formulas for the mean and the standard deviation, I'll put a little box around them. These formulas hold regardless of sample size. You can always apply them to the sampling distribution of the sample mean. So you don't need a specific sample size to use them. Where sample size does become important is if I ask you, do you think the sampling distribution is normal or follows a bell curve. So there are two conditions under which the sampling distribution will be normal or close to normal. The first one is if your population was already close to normal. The second one is if your sample size is large. So would we expect that to hold here? No, we would not expect normality. And the reason for that is twofold. Firstly, the population is skewed. In other words, it's not close to a normal distribution. That's the one condition under which we would have normality. And secondly, the sample size is small. Now, if you watch the video from yesterday, you will know large or small sample size is kind of a relative idea, but for the purpose of this class, we'll use 30 as a threshold. So if your sample size is less than 30, we're going to consider it small. If it's 30 or larger, we'll consider it large. Bottom line is, in this instance, we wouldn't expect the sampling distribution to be normal because neither of the conditions are met. Our population was not close to being normal, and our sample size was not large. What happens if I repeat all of these calculations for a sample of size 50? So the formulas for the mean and the standard deviation are unchanged. The mean is always just the mu value. The standard deviation is always given by sigma over square root of n. So in this case, it's just the value of n has changed. So instead of dividing by square root of 5, we're dividing by square root of 50, which is 7.071. So if we do this division and round to 2 decimals, our standard deviation is 1.13. Now, in this case, would we expect the sampling distribution to be normal? Yes. In this case, we can expect the sampling distribution to be at least approximately normal. Because even though the population is skewed, the sample size is large. So you don't need both conditions to hold, you just need one of them to hold, and that'll tell you that the sampling distribution is well approximated by the normal. You either need to start with something that's normal or close to normal, and the skewness tells us that it's not, or you need a large sample size. Does anyone have a question about problem 1? I'll give you a few seconds here. Okay, let's look at our next example problem. A population that is nearly symmetric has a mean of 50 and a standard deviation of 20. A sample of 16 observations is taken and the sample mean is calculated. State whether the sampling distribution of the sample mean can be considered normally distributed. Let's answer that question before we look at what else is being asked. So in this case, can we reasonably assume normality? The answer is yes. The population is symmetric. And so you don't even have to look at sample size. The sampling distribution should therefore be close to normal. Kind of regardless of sample size. So if we have normality, then the 68, 95, 99.7% rule applies. And what that looks like in the context of the sampling distribution of the sample mean is it's centered at mu, and then in each direction, we're continually adding or subtracting the standard deviation, which is given by sigma over square root of n. So what that means in this case is we need to know what the mean is. The mean is just the mu value always. And we need to know what the standard deviation is, sigma over square root of n. Which in this case is 5. So if you are therefore visualizing what the 68, 95, 99.7% rule looks like, you would have a bell curve centered at 20, and then you would have increments the size of the standard deviation, which we've just calculated to be 5. So this would be 25, 30, 35, and in the other direction, 15, 10, and 5. And hopefully you remember that means like the inner two values, 15 to 25, therefore represents where 68% of our sample averages will lie. So what this tells us is if someone goes and takes a sample from this population, they have a population that's symmetric, has a mean of 50 and a standard deviation of 20, and they go and take a sample of size 16 and calculate the sample mean, what you know is 68% of the time, the sample mean that they calculate will be somewhere between 15 and 25. 95% of the time, it'll be between 10 and 30. And 99.7% of the time, so almost always, not quite always, but almost always, it'll be between 5 and 35. So it gives you a way of visualizing what will happen when someone takes a sample from the population. That's the point of this. It's really something that's used in the planning stage of a survey or an experiment where it helps people conceptualize what range of values will they be able to observe if they have some information about the population. So any questions here about example number 2? See, I may have a question here. Oh, did I mess this up? I did mess this up. I apologize, my bell curve here, the mean was 50, I should have centered it at 50. So let me correct that here. I am very sorry. It should be centered at the mean value, the mu value of 50. And then it increases and decreases by increments of size 5. So the mu value here tells us what the center is. Don't know why I messed that up. I'm really sorry. And the standard deviation tells us what the increments are on our ruler. So if I can correct what I said earlier, so this means 68% of the time, the average will be between 45 and 55. Almost always, like 99.7% of the time, it'll be between 35 and 65. It'll be very rare for someone to go and take a sample from this population. Importantly, a sample of size 16, right? We're doing a calculation for a specific sample size. It'll be very rare that the average you get, if you sample 16 individuals or 16 units from this population, almost never will that average be below 35 or above 65. Yes, it can happen, but it'll be rare. Any other questions? And again, I'm sorry for centering that bell curve in the wrong spot. So I have a question here asking if the 68, 95, 99.7 rule, how that links up to confidence intervals and if it only pertains to the average. So the answer to that question is no, it does not just pertain to the average. It comes up in different contexts. Today we're talking about it in the context of the average, but we also had the same rule when we were just talking about a normal distribution, and we had a variation of it when we were talking about a proportion. So so if we're talking about a sample proportion, for example, there we would know that our mean would be P and our standard deviation would be given by the square root of P times Q over N. So then if we were dealing with a sample proportion, the rule would say, oh, the bell curve would be centered at P, and then you would have your increments going in either direction plus square root of PQ over N, and in the other direction minus square root of PQ over N. In both instances, it does have a connection to confidence intervals because the number of steps you take, 1 step, 2 steps, 3 steps, that's equivalent to the Z star value that comes up for confidence intervals. So you can use this rule to either construct a 68% confidence interval, a 95% confidence interval, or a 99.7% confidence interval. The Z star is just telling you how many steps you take. So yes, there is a connection between all of these different quantities. And I guess I don't want to spend too much time on that right now, but if anyone has further questions about that, I'm happy to discuss that at the end of today's Zoom session. So let me move on. I'll just make a note here that this last part wasn't relevant to the specific problem. Is not part of question number 2. Okay, so let's look at number 3, which is a sample of 15 observations is taken from a normal population. So here's our sample size, and we start with a normal population. And now we're being given information about the sample. We're told the sample has a mean, y bar equal to 13.5, and the sample has a standard deviation, S, equal to 5.3. So first thing that's being asked of us is calculate the mean and the standard deviation of the sampling distribution of the sample mean. So the mean is always given by the mu value, and the standard deviation is always given by sigma over square root of n. So the mu value is unknown, and we know the sample size, but the sigma value is unknown. Remember, these are quantities about the population, not about the sample. So that kind of leaves us in a spot where no calculation is possible here. If we do not know what the population mean is, and we don't know what the population standard deviation is, then we can't calculate the mean and the standard deviation of the sampling distribution. Now, what can we do? Part B is asking for the standard error of the sampling distribution. And the standard error is a way of approximating the standard deviation. So when we can't calculate the standard deviation because we don't know what sigma is, we can calculate the standard error, which tries to approximate that for us. Standard error, which we also sometimes write as standard error of y bar, the formula looks a whole lot similar, except it's s over square root of n. So in this case, 5.3, and our sample size is 15. So 5.3 divided by that square root of 15 is 3.873. So this is 1.37 to 2 decimal places. So there's our standard error. It's not exactly the same as standard deviation, but if we don't have the sigma value, it's our best guess. It's an approximation of what the standard deviation is. So that's what standard error is used for here. And again, just thinking back to proportions, there you also have a standard deviation formula and a standard error formula. And the one you use depends on whether you know the population proportion or the sample proportion. So same idea. Standard error is just an approximation of standard deviation. And then part C asks, would we expect the sampling distribution to follow a normal distribution or a student's t-distribution? Explain your answer. So this is where that result of Gossett, the brewer, comes in. Gossett was working in a situation where the population is normal, but you use standard error and not standard deviation. So even if you start with a normal population, if you're having to use standard error because the standard deviation information is not available to you, then that means the sampling distribution will not be normal. That means the sampling distribution follows students' t-distribution. And I very briefly at the end of the lecture touched on how we construct a confidence interval from here. We'll revisit that again. I do have one more example problem that helps us get at calculating the critical value, the T star value that shows up in this confidence interval formula. So in all of this, we can still visualize a bell curve. Students' t-distribution still follows a bell curve. The tails are slightly different, but you don't have to worry about drawing different tails. You can just draw a bell. And the t star value we're trying to find is the value where if we have negative t star and positive t star, the area between them on the bell curve is C%. So since the total is 100% and there's C% already accounted for, that means in each of the tails, we are going to have 100 minus C% divided by 2. That's important here. The 3 add up to 100%. So at the back of your book, in the appendix, there is a T table. You'll see here it's called Table T on page A109. So this table is how we find the T-star critical values. And what you'll see here is the table, the column headings. There are actually 2 headings. One says 2-tailed probability, one says 1-tailed probability. And you'll see the 2-tailed is just always double what the 1-tail is. So if the 1-tail is 0.1, the 2-tail is 0.2. If the 1-tail is 0.005, the 2-tail is 0.01. It's just been doubled. All that refers to is on this bell curve, if you just calculate the area in one of the tails, or the probability in one of the tails, then you're only going to use the 1-tailed value. If you calculate it on both sides, then you're going to use the 2-tailed value. So both will get you to the correct answer. You just have to consistently make sure you're either using 1-tail or 2-tail. So let's look at an example. Let's say you are using 90% confidence, your sample size is 15, and you want to find the T-star value. So what this tells you here is if we're trying to find the T-star value, 90%, it's easier here working with decimals, is 0.9. So how much is left? In the 2 tails combined, 0.1 is left. So if you divide that by 2, that means each of the tails now has 0.05. So we can either go to the table and look up a 2-tailed value for 0.1 or use the 1-tailed column for 0.05. It's the same column. So this tells us which column to use. The other question is which row to use. And the row is called degrees of freedom, and the formula for that is just sample size minus 1. So we want to go to the T-table and find the entry that corresponds to this column and this row. So we're looking for the column 2-tail 0.1, 1-tail 0.05, and we said the row value is 14 degrees of freedom. And so we're just looking for where these intersect. So that's our T-star value, in this case 1.761. Let's do the next example here. Let's say you were working with 99% confidence and your sample size is 36. So again, it can be helpful to visualize that bell curve. You have a negative T-star and a positive T-star, and 99% confidence means that the part in the middle of your bell curve is 0.99, which means the two-sided value is everything that's left, which is just 0.01. And if you were to divide that by 2, it would be 0.005. So this is again telling us which column we're going to use. Degrees of freedom, sample size -1, that tells us which row to use. So we need the column that's 0.01 and 0.005, and we need the row that's 35. So let's head over to the table. Here's the column, 0.01 and 0.005. And we're coming all the way down to 35 degrees of freedom. So we're looking for where these intersect. So in this case, our T-star value is 2.725. And I think I'm just going to do one more of these. I'm going to jump to number D, which says we have 80% confidence and our sample size is 29. So every time you can go through the same steps. Visualize your bell curve. You know you want to have confidence between the T-star values, in this case equal to 0.8. So what's left for the two tails? In this case, that's 0.2, which means in one of the tails, we have 0.1. And our degrees of freedom in this case would be 28. So this is our row, this is our column. Let's head over to the table. Let me do the same color I was just writing in on the other sheet. So column 0.2 and 0.1, the row we said has to be the value 28. So we find where those intersect one another, and that's our T-star value. So in this case, T-star is 1.313. So I know at this point, we are just looking at, how to find the T-star value, and it doesn't have a lot of context, but it's important for calculating a confidence interval. So that's what we will be looking at next time.